Hi, I'm Aditya, and I'll be talking about my work on building a machine learning model to detect non-vocalizing species in fine-scale audio data. The talk is mainly split into two parts. One involves detection of multiple species, and the other is more targeted at single species detection. More details on that later. Let us first understand the dataset that we will be working with. The data was collected at three sites, all inside IISc. The sites have varying levels of human activity and noise. All the data was collected thanks to Shubhabat. Every morning, an hour of audio data was recorded, and all the birds that were seen and heard in that duration were noted down. This was done for 64 days across many months. Specifics of the data set are given on the slide. In order to train machine learning models on audio data, we first need something called a feature. We will be deriving features from two models, BirdNet and VTGs. BirdNet is the model used by apps like Merlin that might be familiar to some of you. These models use convolutional neural networks and generate feature vectors, which contain information about motifs in the audio file. We will be working at a 1 minute resolution. That is, our RD files are split into many 1 minute resolution files, which are the resolution at which our data is collected. All the feature vectors generated by neural net models will be averaged for that whole 1 minute duration. KNN is a supervised learning model that classifies information based on identity of the n nearest neighbors. In this example, the majority of the nearest neighbors are green for the question mark point. Hence, it will be classified as green. This model can generate multi-class, that is, multiple species predictions for a feature vector. Some more ML terminology. Ground truth is a set of entries containing our dataset, and these metrics like false positive, false negative, and true positive are important to quantify the predictions of our model. Please ask me in chat if something is unclear. We train these KNN models on four folds. This basically means that we section the data into four parts, train the model on three of them, and test it on the fourth part of the data. We iteratively do this for all the four folds that we have generated. All the results in the future sites are results after averaging the scores across all the iterations of the four folds. Time for some results. What I mean by multiple species identification is that the model tries to predict all the species that are found within an audio file in one go. When we do multi-species identification, our model gives roughly 60% precision and very low recall. The low recall tells us that a lot of the data present in our ground truth is actually missing in our predictions. We try to improve this later with our single species classifiers. Another important thing to check is that if our data has information in the first place. We carried out permutation tests to check this. Features and their species ID labels are randomly shuffled, and the same pipeline is carried out on all of them to get the scores for random data. The histogram that you see is randomization of scores, and the dotted line is the score of the true data set. Our true score is significantly different than the distribution of the random scores. So that means that our true data actually has some important information about non-vocalizing species. So let us look at making multiple single species models. That is, for detection of each species, a new model is generated. In our data, all species are not present equally. Hence, we need to select a subset to run these models on. If a bird species occurred in more than 92 1-minute audio sections, we select that species to train our individual models on. The selected species are shown on the slides. For each species, we randomly sample instances where it is not present to create the negative data set. Hence, our classification task is Boolean. The model predicts if a bird is present or not in a given audio file. The size of the negative data set is equal to the positive data set. Let us look at the results for our models. Precision and recall are almost equal and high. This is a good sign. The scores range from 60% to 80%, which isn't perfect, but considering that the model is making predictions of non-vocalizing birds from audio file that takes soundscape data, these are good scores. Again, doing permutation tests on individual models also tells us that the data has quite a lot of information, as the p-value is 0 in these plots. Final conclusion is that it is possible to make predictions of non-vocalizing birds from soundscape data. I believe the model can be significantly improved by incorporating more varied data sets across multiple different sites. This provides a new way to monitor birds, which is easy to deploy, and also hints at the fact that soundscapes carry more information than just vocalizations. I would like to thank Shubha for collecting this data set. I would also like to say thanks to Arpit, Professor Rohini Balakrishnan, and Professor Sarab Sethi for their guidance. Thank you. Please drop any questions in the chat.